A strong earthquake struck western Japan at 9:19 p.m. The Japan Meteorological Agency has issued a tsunami advisory for Miyazaki and Kochi prefectures. Japan's recent 6.8 magnitude earthquake was powerful enough to shake more than just the land. It may have disturbed the colossal magma chamber of the world's largest caldera. This isn't just a local tremor, it's a seismic event with the potential to awaken a sleeping giant. Could the intense forces unleashed by this earthquake destabilize the magma beneath, setting the stage for a massive eruption? And if so, what does that mean for the surrounding region and even the planet? Let's find out in today's episode. Attention! This video is created with the purpose of raising awareness about the potential geological impacts of the recent earthquake in Japan and its connection to one of Earth's most massive and complex volcanic systems. Our goal is to provide accurate, science-based insights to help viewers better understand these natural phenomena and their potential implications. It is not intended to spread fear or sensationalism, but to foster awareness, preparedness, and informed discussions about the dynamic forces shaping our planet. Knowledge is the first step toward safety and resilience, and we aim to empower our viewers with the facts they need to stay informed and vigilant. The world stood still with a mix of awe and unease as a powerful 6.8 magnitude earthquake struck Japan late Monday night. This seismic event sent tremors rippling not only across the densely populated land, but deep into the Earth's crust, disturbing subterranean forces that are as ancient as the planet itself. Earthquakes are not uncommon in Japan, a country sitting along the infamous Pacific Ring of Fire, but this particular event has captured the attention of geologists and volcanologists worldwide. What makes this earthquake particularly concerning is its potential impact on some of the region's most significant geological structures, including the colossal magma chamber of the Appalachian Caldera, the largest known caldera on Earth. This raises a critical question. Could this earthquake be a precursor to a greater geological event? The Appalachian Caldera, an awe-inspiring yet largely hidden geological feature, lies beneath the vast expanse of the Philippine Sea. Its name, derived from Appalachia, the Filipino sun god, is fitting for a structure of such immense scale and power. Spanning an estimated diameter of 150 kilometers, the Appalachian Caldera is a true giant among calderas, far surpassing even the infamous Yellowstone caldera in size. Unlike most calderas visible on land, Appalachia remains submerged, its vastness concealed, beneath ocean waters discovered only in recent years with the advent of advanced undersea mapping technologies. The formation of the Appalachian Caldera is a testament to Earth's violent and dynamic history. Scientists believe it was created millions of years ago during a series of cataclysmic volcanic eruptions. These eruptions, likely among the most powerful Earth has ever experienced, would have ejected colossal volumes of magma and volcanic gases, leading to the collapse of the Earth's crust above the emptied magma chamber. The sheer energy released during these eruptions would have caused widespread climatic and ecological impacts, potentially altering global temperatures and triggering mass extinctions. Today, the Appalachian Caldera represents a sleeping giant. Its magma chamber, buried deep beneath the seabed, contains immense potential energy held in check by the overlying layers of rock and water pressure. While it has been dormant for millions of years, its size and explosive history place it among the most significant volcanic features on the planet. A disturbance of this system, even a minor one, could have profound consequences, not just for the surrounding region, but potentially on a global scale. The proximity of Monday night's earthquake to this geological titan adds an unsettling layer to an already dramatic event. The earthquake, while occurring hundreds of kilometers from the caldera, has raised concerns about the potential for seismic waves to interact with the delicate balance within Appalachia's magma chamber. Such interactions, while not yet confirmed, are a stark reminder of how interconnected Earth's geological systems truly are. Could the tremors that rattled Japan have stirred a beast lying beneath the Philippine Sea? Only time and meticulous observation will tell. The earthquake that shook Japan late Monday night was a stark reminder of the country's precarious position along the Pacific Ring of Fire. The 6.8 magnitude quake originated near the Ryukyu Trench, a tectonic boundary where the Philippine Sea Plate is steadily being forced beneath the Eurasian Plate, a geological process known as subduction. This process is responsible for the region's intense seismic and volcanic activity, often triggering catastrophic events such as earthquakes and tsunamis. Initially reported as a magnitude 6.9 by Japan's meteorological agency, JMA, the quake's intensity was later revised downward to 6.6. Despite the recalibration, the event's power was formidable, equivalent to hundreds of thousands of tons of TNT. The earthquake struck at 9:19 p.m., with its epicenter located at a depth of 30 kilometers, 18.6 mi under the seabed near the southwestern island of Kyushu. Residents in coastal areas were immediately put on high alert, with tsunami advisories issued for Miyazaki and Kochi prefectures. Within 30 minutes, tsunami waves estimated at up to 3.2 feet were reported, though the actual waves at Miyazaki Port measured just 8 inches. Advisories were lifted shortly before midnight, but not before underscoring the swift and decisive actions taken to protect lives. Casualties from the quake were minimal compared to Japan's history of seismic disasters. A man suffered minor injuries after falling downstairs, and train services were temporarily halted, stranding passengers. Yet the nation's resilience and preparedness shone through. Strict building regulations and advanced early warning systems likely prevented more severe outcomes. The JMA cautioned residents to remain vigilant for aftershocks, landslides, and falling objects in homes, as the possibility of secondary disasters loomed in the quake's aftermath. While the immediate human impact of the earthquake was mitigated by Japan's advanced preparedness, the potential geological repercussions are profound, particularly regarding the region's intricate magma systems. Chief among these is the Appalachia Caldera, a titanic feature submerged beneath the Philippine Sea. As the largest known caldera on Earth, spanning an astounding 150 kilometers, its immense magma chamber holds a staggering amount of potential energy. Although located hundreds of kilometers from the earthquake's epicenter, near the Ryukyu Trench, seismic waves from the quake could propagate over vast distances, potentially disturbing the delicate balance within Appalachia's subterranean system. When an earthquake occurs, it releases energy that radiates outward in the form of seismic waves. These waves travel through the Earth's crust and mantle, varying in speed and impact depending on the medium they pass through. Two primary types of seismic waves are involved in this propagation: P waves, primary waves, and S waves, secondary waves. P waves are the fastest seismic waves, traveling at speeds of 6 to 8 km per second through the Earth's layers. These compressional waves move in a push-pull fashion, compressing and decompressing the material they pass through, much like a slinky being stretched and released. P waves can travel through both solid and liquid layers of the Earth, making them capable of reaching even the most distant geological structures, including submerged magma chambers like Appalachia. When P waves interact with a magma chamber, their rapid oscillations can induce minute changes in pressure within the surrounding rock, potentially altering the magma's state. For example, the compressional force of P waves can momentarily compact the chamber walls, leading to minor shifts in magma dynamics. This disturbance, though often subtle, can become significant if the system is already primed for activity. S waves follow P waves but travel more slowly at about 3 to 4 km/s. Unlike P waves, S-waves move in a side-to-side or up-and-down motion, causing more intense shaking. However, S-waves can only travel through solid materials, as liquids do not support their shearing motion. When S-waves reach the vicinity of a magma chamber, they can exacerbate the stress on surrounding rocks, amplifying deformations in the chamber's walls. This increased stress may encourage magma movement, particularly if the system is under high pressure. The combined action of P and S waves can reverberate through a caldera's magma system, especially one as vast and complex as Appalachia. These waves can interact with magma conduits, reservoirs, and gas pockets, triggering dynamic responses that range from subtle shifts in magma distribution to potential unrest visible at the surface. Zones potentially affecting volcanoes along the same plate boundary. Additionally, global seismic events such as the 2004 Indian Ocean earthquake have been observed to trigger minor volcanic activity in distant regions, showcasing the interconnectedness of Earth's geological systems. However, this interconnectedness is not akin to a literal network of linked magma chambers. Each volcano operates within its localized environment, shaped by unique geological and tectonic conditions. That said, disturbances such as seismic waves or shifts in tectonic stress can ripple outward, indirectly influencing other systems. The Appalachia caldera, given its immense size and volatile history, remains a critical point of focus. While no immediate volcanic activity has been reported following Monday's earthquake, the potential for triggered volcanism cannot be dismissed. Even subtle disturbances caused by seismic waves could destabilize its magma chamber, especially if it is already near a critical pressure threshold. Continued monitoring of the region will be essential, as the full extent of the earthquake's impact on this sleeping giant may only reveal itself in the weeks and months ahead. Likewise, due to their proximity to the earthquake's epicenter, these volcanoes could be sensitive to even the smallest shifts in the tectonic balance. Mount Sakurajima, one of the most active volcanoes in Japan, has a long history of dramatic eruptions. Located near the city of Kagoshima in Kyushu, its most significant event occurred in 1914 when a massive eruption connected the former island to the Osumi Peninsula via lava flows. This eruption, one of the largest in Japan in the 20th century, resulted in widespread destruction, including the loss of lives and the displacement of communities. Frequent smaller eruptions continue to this day, with ash plumes regularly disrupting life in Kagoshima.